Muito obrigado pela presença de todos. Para nós, do Instituto de Investigação em Imunologia, o INCT e é um prazer recebê-los, assim como a Faculdade de Medicina da USP, e receber, sobretudo, essa figura tão importante e que nós somos todos curiosos para ouvir, que é o professor Irun Cohen. Eu particularmente, conheço o professor Irun Cohen há muitos e muitos anos, e os nossos encontros se tornaram regulares, porque nós sempre fazemos questão de, pelo menos num congresso chamado Congresso Internacional de Autoimmunidade, que é organizado por um amigo em comum chamado Yehuda Schenfeld, e a gente sempre se encontra lá, se não tiver a oportunidade de se encontrar em outras ocasiões. Mas eu conheço o professor Irun Cohen desde o tempo que eu era aluno de doutorado, por trabalhos que ele fez relacionados ao papel de interferon e resposta imune, expressão de HLA, etc. Então, o professor Irun Cohen, ele é formado em filosofia, o que deu um viés interessante para o que ele ia fazer depois, e depois em medicina, e ficou pediatra. Mas se dedicou à imunologia desde o início. Ele transferiu-se para Israel, onde ele trabalha no Instituto Weizmann, e foi sempre uma referência de imunologia, não só pela qualidade dos trabalhos, mas pelo pensamento que ele tem. Ele sempre agrega muito valor às pesquisas que ele faz, tentando interpretar e tentando dar uma ideia geral do sistema imune, como é que funcionaria, através das suas pesquisas. E eu acho que é muito importante vocês verem isso e tentarem entender esse segundo pensamento que ele tem nos experimentos, tentando dar uma lógica para o sistema. Ele é extremamente conhecido e citado. Em 2002, foi o pesquisador mais citado pelo ISI. Além disso, é uma grande figura humana, que vale realmente a pena conhecer. E é com muita satisfação, há muitos anos que nós o convidamos aqui. E eu estava agora mesmo lembrando para ele que ele veio Israel, Porto e do Porto para cá. E eu lembro que há um tempo atrás nós estávamos reunidos tomando vinho do Porto no subsolo, num restaurante que era no subsolo lá no Porto, estava muito agradável. E ele disse, olha, finalmente não é tão difícil assim vir para o Brasil, porque vir até aqui foi tranquilo, de Israel, e daqui eu sei que tem um voo direto para São Paulo, que são 10 horas. Então acho que dá para fazê-lo fazendo uma escala em Porto. E foi o que ele fez, ele passou uns dias no Porto e veio para cá. E aqui está conosco. E espero que vocês aproveitem esses 3 dias que ele estará aqui conosco, depois ele vai para o congresso da SBI. So, Irun, I was just telling them what a great pleasure for us to have you here. For a long time we have been inviting you to come, and we are sure that you'll enjoy this trip, and this will make you come back if Yael, that was unable to come this time, and I'm sure she'll also enjoy coming here. Thank you very much for your time. I think you're ready for your talk, and we are going to work here in such a way where you give your talk, and then we invite some of the researchers working in immunology from different institutions to make questions, comment, and just to animate, I would say, the discussions after the talk. Thank you very much. It's really my pleasure.
Thank you, George, Khalil, and the III, and Veronica Coelho for bringing me to, or allowing me to come to Portugal to Brazil, excuse me, I'm on the way from. My jet lag still has me in Porto, but I'm here. I'd like to tell you about our, let's say, the success of our clinical trial in developing a treatment that looks like it arrests the autoimmune destruction of islet cells, the process that leads to the development of type 1 diabetes. And we've just completed a phase 3 clinical trial, a large phase 3 multi-center clinical trial with some success, with a lot of success. And now there's a confirmatory phase 3 that's well underway. And I hope that will also succeed. But even at this point, there's something to talk about. And what I'm going to try and do is describe something about the treatment, which is an exercise in translational research. You'll hear something about how we made a fortuitous observation which led to about 20 years of research. So you'll see something about the thinking, at least our thinking, which went into translation of a very basic observation into something that looks like it could be clinically important. In addition, I'd like to describe what we've learned about the immune system in this translational endeavor. In other words, it's not only that we came across a peptide that can influence the way the immune system behaves in the case of an autoimmune disease, but in doing this, we've discovered, I think, important things about the immune system itself. Because the basic question is, why should a peptide turn off an advanced destructive autoimmune response? So you'll hear really intertwined together 2 or 3 different lectures. One is a story about doing translational science. One is a story about clinical results. And one is a story about how the immune system is built so that it listens to our peptide. Okay, so that's the title. Now, traditional therapy is based on immune suppression, particularly in the case of autoimmune diseases. Autoimmune diseases are caused by the activity of the immune system. So the idea has been if the immune system is causing the disease, let's suppress the immune system. Those things work. Lately, there's a lot of advances in antibodies to TNF-alpha and T cells and B cells, and there are good effects on disease, but there are also very serious side effects. By suppressing the immune system, we pay a heavy price, and not just the cost of the drugs. And I'm going to talk about an HSP60 peptide called Diapep. We called it P277 for the treatment of type 1 diabetes. And this is an example of as I hope you'll see, using the immune system's own molecular language in dialogue with the body to change its behavior. Now, dialogue therapy is based on the idea that living systems, complex living systems, really regulate themselves. They have to regulate themselves. This is in medical science, it's clear that the system has to know what to respond to and what not to respond to. And so it means that the system being robust to a lot of noise and a lot of signals that other systems respond to is still extremely sensitive to the signals that the system uses to make its own decisions. So there are control signals, adaptive control signals in all systems. And the idea is to try and discover which signals the immune system uses to talk to the body and supply those molecules such that in the case of an autoimmune disease, the disease process will be down-regulated or disappear. Now, an advantage not only of, in this kind of approach of getting effectiveness, but if you can avoid suppressing the immune system and just getting it to behave with respect to the particular process that is causing the disease, but otherwise leave the system intact, you not only get effectiveness, you get safety, because you don't punish the system, you don't inactivate the system, you let it go on. And the example, as I said, is HSP60, or a heat shock protein, and it's the peptide that we discovered from it. Now, how did we get into HSP60? And this is the beginning of an experience in translational medicine. We were interested in the spontaneous development of antibodies in the course of diabetes in NOD mice, antibodies developing to insulin. So we were interested in anti-insulin antibodies, and we were also studying anti-idiotypes, antibodies that bound the anti-insulin antibodies. And we were looking at NOD mice, female NOD mice. At the time, about 60 or 70% of these mice would develop diabetes by about 180 days of age, and which meant that 30 or 40% would not develop diabetes. So the idea was, let's take, starting at 20 days of age, we'll get serial bleeds on these mice, and at the end of the time, we'll know which ones developed diabetes and which didn't develop diabetes, and then go back and test the sera, looking for antibodies to insulin and anti-idiotypic antibodies to insulin. So here are the results in two mice. Mouse A did not develop diabetes, and mouse B did develop diabetes. And these curves at the bottom are antibodies to insulin and the anti-idiotype. This is what we were looking for. But we needed a control. And at the time, Willem van Eden was a postdoc, and we were looking at a process of arthritis, adjuvant arthritis in rats, and discovered that there were reactivities to HSP60 in the arthritis model. And since we had HSP60 on the shelf and we were looking for control, we put it into the diabetes model as well, and we're very surprised to see that much more prominent than the antibodies we were looking for, which were the insulin antibodies, were antibodies to HSP60. And in fact, not only were there antibodies to HSP60, there were spontaneous T cell responses that preceded the diabetes and the diabetic mice. Then having technology for, this is in the early 90s, having technology for developing T cell clones. We isolated clones of CD4 T cells that were able to recognize HSP60 and home to the pancreas and appeared to be associated with the diabetes. But we could also use those clones as probes and ask them to reveal what do they see in HSP60? What are they responding to? And taking genetic deletion mutants of the molecule and peptides and so on, we were able to discover that one of the clones, which recognizes whole HSP60, which homes to the pancreas, which could even adaptively transfer hyperglycemia and insulitis, that C9 clone recognized a peptide from the HSP60 sequence, which we called P277. We called it P277 because it came out of the peptide unit. The bill number was P277, or it was 277, and I like the number 277. Sounds like a lucky number. So let's call it peptide 277. Its sequence is 458. Okay, so we stumbled on HSP60 that was originally related to arthritis, different epitopes, not the same as this. But then we discovered very unexpectedly that there was a relationship to NOD diabetes. And now we had to make a decision. Do we go on and study this problem or this observation? Or do we go back to doing the things that we had been doing and we were busy doing? Now, one of let's say, one of the themes of the laboratory based on something we call T-cell vaccination, but that's another talk. One of the themes is that elements that are involved in pathogenesis, in the pathogenesis of autoimmune diseases, can also be used to downregulate the disease. Without knowing too much about it, we knew that if we discovered a peptide that was targeted by diabetogenic T cells, by pathogenic T cells, what would happen if we just injected the peptide? The peptide is a target of an effector T cell, but what would the peptide by itself do? This is a question that really doesn't have a hypothesis. It's a question that comes to mind when you discover a new toy and you want to see how it works and you want to play with it. Now, it's written in all the textbooks that science advances by hypothesis testing. But I would say that and hypotheses do bring us to good science, but hypotheses usually come after we know something. And discoveries usually come when we don't know something, and often from the pleasure of playing around. So we had a peptide, and we knew some of its properties recognized by a pathogenic T cell and so on. But let's inject the peptide. What do we have to lose? Maybe something will happen. So we injected the peptide, and the incidence of diabetes went down 60 or 70% with a single injection of the peptide. And so now we had another problem. Do we invest in, I mean, is this serious? Because you can downregulate NOD diabetes with all kinds of treatments. There have been papers showing that in 100 different ways, if you manipulate the NOD mouse, you can reduce the incidence of diabetes, even by injecting bacteria, even by injecting complete Freund's adjuvant. So we injected a peptide and early on in age, and there was an impact on the development of diabetes, spontaneous type 1 diabetes in the NOD mouse. So what? Is this a discovery, or it's just the outcome of a game? Then we said, okay, if this is serious, then it's not enough just to abort the process by treating 4-week-old NOD mice. Let's treat mice that are already diabetic. If we can turn off the disease and save mice from death from diabetes, mice who already have diabetes, then maybe it's not just a game. So right on, again, in the early, this paper is from 1994, which means we did the experiments in 1993, after the discovery in 1991. And we injected NOD mice at 12 weeks of age when they're just going to get diabetes, and at 15 weeks of age when half of them already have hyperglycemia, and also at 18 weeks of age when almost all of them have hyperglycemia. And in each case, we saw that the animals that got the placebo, most of them went on to die, but the animals that got a single injection of 100 micrograms of the peptide, very few of them died. This one died, but already had a very high hyperglycemia. But the ones that had hyperglycemia, it was frozen. They didn't go on to die. Some of them lost their hyperglycemia, but others just maintained hyperglycemia without treatment and without dying. So that was an important step in the translational process, because we went right to what we thought would be a test of the importance of the observation, and we saw something that encouraged us to relate to it seriously. Now I want to jump ahead and describe something about the results of the next 20 years of research in general that relate to HSP60, and then we'll go back to the diabetes story. What we now know about HSP60, this is a review by my colleague Francisco Quintana. We published in Trends in 2011, and it's a summary of work by a lot of different laboratories looking at HSP60, and what we see is that HSP60 and its peptides are central in a network of immune cells. The various immune cells, B cells, dendritic cells, macrophages, Tregs, effector T cells, all kinds of T cells, B cells, and monocytes have different receptors for HSP60 epitopes. What's more, the concentration of HSP60 and the different cells that it interacts with can lead to inflammatory, pro-inflammatory reactions, increase in IL-12 and TNF-alpha, interferon, and so on. But it can also lead to anti-inflammatory cytokines, TGF-beta, IL-10, again depending on concentration, depending on cell type. But we now know that HSP60 is a key element in, let's say, in presenting a signal to different aspects of the immune system. The HSP60, in a way, is a kind of a biomarker, and it's easy to understand because heat shock proteins, the way they're expressed, how they're expressed, is an expression of the state of stress of cells. Cells in the body, the bacteria that are attacking the body, all the interesting things that go on in the body that the immune system has to know about or needs to know about if it's going to perform its function, somehow lead to a modification in the expression of stress proteins. So stress proteins are good candidates for information about the body, and maybe it's no wonder that the system is outfitted with so many different cells and molecules that look at it. Because the immune system, to manage inflammation, really has to be involved in a kind of a computation of the state of the body. So there are immunogenic biomarkers that tell the system about infection, this vaccination, trauma, neoplasia, aging, and so on. A series of signals that we can call immunogenic biomarkers that are sensed by cells of the immune system, both through innate and adaptive receptors. The interactions among these immune cells leads to immune response outputs that, in chemical terms, molecular terms, we call inflammation. which involves apoptosis or the opposite, proliferation, angiogenesis, differentiation, migration, and so on. So the immune system is sensing signals from the body, processing these signals, computing the state of the body, coming out with an immune response, an inflammatory immune response. And this immune response feeds back on the state of the body, and it also feeds back on the immune system itself. So there's a very complex set of interactions that the immune system uses to organize itself through the experience of the body in dealing with the world. Now, what we discovered early on is that the P277 peptide of HSP60, if we saw that HSP60 can do pro-inflammatory as well as anti-inflammatory reactions, the peptide itself was devoid of pro-inflammatory. If we take the production of IL-12 by macrophages in vitro, dependent on toll-like receptor 4 and the production stimulated by HSP60, we can see that HSP60 will stimulate IL-12 in macrophages that have intact TLR4, but not with mutant. LPS, of course, also activates through toll-like receptor 4, but P277 by itself does not activate the production of IL-12. So by going to the peptide, we could discriminate between the anti-inflammatory effect of HSP60, which is what we want in the case of an autoimmune disease, from the pro-inflammatory effects, which, by the way, is something that we might want in tumor immunotherapy, but that's a different story. So let me jump to the end, which is the clinical trial, and then we'll go back and sort out why this peptide works. So I'm briefly going to describe a phase 3 clinical trial, 40 centers in Europe, Israel, and South Africa, 457 patients, young adults, recently diagnosed, who have residual C-peptide. Why did we take individuals who we know have diabetes? Because a preventive study has several problems. One is that you need a lot of patients because you don't really know who's going to get the disease. It's very costly. And secondly, you're going to end up treating people who aren't going to get diabetes, so you're exposing people to treatments that they don't need. If you take people who are already sick, then you're more ethically justified in giving them treatment because they seek the treatment. You don't knock on somebody's door and say, "Mother, you don't know it, but your baby's going to get diabetes unless blah, blah, blah." But these are people who are seeking aid. Why residual C-peptide? Because C-peptide is a marker for us of endogenous insulin secretion. So people who have residual C-peptide are people who have some beta cells left over. Even though they're diabetic, they have residual beta cells. And by the treatment, we can see if they continue to have C-peptide or increasing C-peptide. It means that we've shut off the destruction, and in the placebo, they continue to lose whatever C-peptide they had. So the treatment here is this peptide, 1 milligram or placebo, subcutaneously once every 3 months. So 4 milligrams a year of a peptide for a period of 2 years, and the patients receive insulin, and we can see how much insulin they need and all kinds of other things. The results at the end of 2 years showed what we were hoping for, safety. There was no difference in adverse effects between the people who got the placebo and the people who got the real peptide. We had preservation of beta cell function by C-peptide preservation, both baseline fasting and stimulated with glucagon. What was surprising for me is that there was increased metabolic control, because I thought in a trial, physicians are very much encouraged to give optimum treatment. And if the physician is giving insulin, or the patient is taking insulin the way the patient should take it, then there should be metabolic control, whether or not they're residual beta cells. But still, we saw that there was better metabolic control if patients got the P277, and they needed less insulin, significantly less insulin, to maintain good metabolic control. And they had fewer hypoglycemic attacks because they didn't have to take so much insulin. So it really made a difference in the disease of people who already were diseased, and these are positive results. So 1 milligram every 3 months, and already you can ask yourself, how can you turn off a whole disease with 1 milligram of peptide, or 3 milligrams, 4 milligrams over a year? Arresting the beta cell destruction, preservation of beta cell function, less insulin, metabolic control. And I'll show you some things. Again, we'll go back to the mice, because we can't do such studies in humans, that the downregulation of the destruction of the beta cells has some very specific aspects. And one of them is that not only is there a change in the way the immune system responds to HSP60, but also in the way it responds to other diabetes-associated antigens. But antigens that are not part of the collective of autoimmune targets in diabetes are not affected. I'll show you what I mean by that. In addition, another very, let's say, surprising aspect is anatomical specificity. There's compartmentalization of the effects in the islets, and less so or not at all in the spleen. Now, let's take a look at the antibodies or T cells. In controls, NOD mice, they make antibodies to whole HSP60. They don't make antibodies to the peptide. They also make antibodies to glutamic acid decarboxylase. They make antibodies to insulin. After they get the peptide, they stop making antibodies to insulin, to GAD, to whole HSP60, and they make antibodies to the peptide. At the point of the T cell response, before they get the peptide, or if they get the control peptide, they have T cell reactivity to P277. That's how we discovered it. They have T cell reactivity to GAD. They also have T cell reactivity to a mycobacterial HSP60 homolog, which here we call MT278, and they respond to mitogen like concanavalin A. After they get the peptide, the T cell response to the 277 goes down. The antibodies, as you saw, went up. But the T cell response to GAD and also to insulin go down, but the response to the mycobacterial antigen stays the same, and the response to the mitogen stays the same. So there's let's say an immune specificity that sorts out which autoimmune targets are important in the disease and which targets should be left alone, like the bacteria. And this we see a distinction in the islets compared to the spleen. So this is a difficult study by Vitaly Ablamunitz, who isolated islet infiltrating T cells with various treatments, treatment of the mycobacterial peptide or the 277 from the islets and also from the spleen, and found that the animals treated with 277, their T cells, they still had T cells in the islets, could not be induced to produce interferon gamma. But in those very same mice in the spleen, there was plenty of interferon gamma. Of course, treatment with the mycobacteria didn't change the interferon gamma response anywhere. So the diapep signals many regulatory pathways. Innate T cell signaling by way of toll-like receptor 2. I'll show you something that affects adhesion, migration. There's an effect via toll-like receptor 2 on Tregs. Again, we go back to humans. There's also an effect by 277 on adaptive receptors, a T cell receptor. Another form of regulatory T cells, anti-ergotypic T cells, we won't go into it, but also on effector cells. And as we saw before, the peptide is a natural regulator. This is data showing that it enhances human T cell adhesion by way of toll-like receptor 4. It inhibits chemokine receptors. It inhibits chemotaxis. Again, I want you to note the low concentrations. These are nanograms per ml. We get effects at 1/10 of a nanogram, 100 picograms, or even 10 picograms. So the system is exquisitely sensitive, and of course the crowning glory was the work of Alexandra, who showed that P277 through toll-like receptor 2 has effects on signal transduction in Tregs, which have effects on signal transduction in effector cells that leads to downregulation of the pro-inflammatory TNF-alpha interferon gamma. So we have some evidence of the varied ways that the body relates to this molecule and to fragments of it. HSP60 is expressed at the site of the action in the beta cells. What I want to close with is something that we've just discovered. As I said this, we used the C9 clone to identify P277. That was a clone we isolated from pre-diabetic female NOD mice, and we used that to probe the HSP60 molecule and got to 277. Now it turns out that the CDR3, the complementarity determining region 3 of the T cell receptor of C9, is not just limited to that clone. It's present in different NOD mice, and as I'll show you, it's present also in C57 black mice that don't have anything to do with diabetes. It's a very prevalent T cell receptor combining region, and it differs from the T cell receptor combining regions of T cells that see foreign antigens like viruses. And in addition, there are anti-idiotypic T cells that recognize the T cell receptors of the T cells that cause diabetes. Now, we don't have time to get into it, but let me just show you female NOD mice, before they get diabetes, the first thing we see is they have spontaneous anti-idiotypic regulators that they lose, and then they develop diabetes. The males who are much more resistant to spontaneous diabetes, they actually boost spontaneously. We don't inject anything here. They boost their anti-idiotypic, their regulatory T cells that are specific for the C9 T cell receptor, and then spontaneously lose that regulatory reactivity, and out comes the diabetes. And in fact, we can downregulate the diabetes with the anti-adaptive transfer of the anti-idiotypic T cells themselves. Now, what ties the story together is that the P277 peptide upregulates the anti-idiotype and downregulates the idiotype. Now that we would probably need another lecture to explain. But the bottom line is that there are a whole series of inbuilt regulatory interactions that are centered around, not only around the HSP60 molecule, but around the T cell receptor that sees that molecule. And if we look at the frequency of the C9 T cell receptor, so this is work done with the laboratory of Nir Friedman, with let's say the present ability to do whole genome sequencing. Nir was able to look at around 400,000 T cell receptors in about 30 black mice, C57 black C mice, and could probe those 400,000 receptors to see, are any of them like the C9 receptor and that's active in NOD mice. And here there are 27 or 28 different B6 mice that are untreated or treated with complete Freund's adjuvant or complete Freund's adjuvant ova, and they all have that idiotype. Not only do they have the C9, they also have T cells that are related to EAE or multiple sclerosis. They have T cells related to arthritis, to allograft reactions, and much less so regarding VSV virus, influenza virus, murine leukemia virus. This is a kind of an opportunistic study. It's not an exhaustive study. It's just taking out of the literature different T cell receptor sequences, and we find that the T cell repertoires of healthy animals have a very high frequency of shared autoimmune associated receptors. This is another way of looking at it. We won't go into this, but what we're coming to appreciate the idea that the immune system is a cognitive system. It has certain pieces of information that it's looking for. It has an inbuilt image of the body in health and in disease, something I've called the immunological homunculus. And what we've done here is I think, an example, at least one example, of how we can use these natural adaptive biomarkers of the system and translate that information into what appear to be effective treatments, effective and safe. Of course, we did it the other way around. We first discovered the peptide and then discovered why it works, which led us to the idea that it really works because it's a biomarker. But that took 20 years and was stimulated by following up the clinical implications of the results that we began at least with serendipity and with fooling around. And of course, a lot of people have been involved in different aspects of the study, and it's been a great pleasure working with these friends. Thank you.
I'd like to invite the people that have been invited for this. Professor Marcelo Barsinski. Professor Marcelo Barsinski, most of you know. He's graduated in medicine. He was a professor of biophysics, and he has been in several places. He's a wonderful researcher in immunology. He has been for many of our good immunologists in the country, and nowadays he works in Fiocruz in Rio after passing through many places. He always has been between São Paulo and Rio. He's a Paulista, but his heart is Carioca. Luiz Eduardo Andrade is associate professor at UniFesp. He's a rheumatologist, and he has a postdoctoral training at Scripps, and has been around for a long time. We have the honor that he's a visiting professor of the School of Medicine, and he spent some time in our service as well. And last but not the least, Verônica Coelho, that is graduated in medicine in Pernambuco. He did residency here. Just after residency, he came to our lab in the mid-'80s when she was still a small child, and she's still there. She did her obtained her doctoral degree under my supervision, but she spent some time at MIT with Tonegawa. And she's very active in the iii, and I thank her for that, and also thank her for organizing all this. She is the one that organized all this meeting. So we have this panel of researchers. I just would like to start with this provocation. How much of serendipity you have in this? I mean, actually, you used the shock protein as much of a control in the beginning, right? Yeah. And it came out that it was tremendously interesting. And how come that you can find some specificity in such a molecule that is so ubiquitous? How these magic peptide...
That's a different question.
Yes, that's the second question. That's the second question. And how this peptide could be specific.
Well, first, the question of serendipity. I think I think the lesson is that a researcher should take the experimental results seriously. Now, I remember when I was a postdoc, and I discovered that normal rats had what looked like reactivities to self molecules. I was doing an experiment. It was a transplantation experiment in vitro, so we were looking at allograft responses, and I threw in a control of self cells. And I saw in vitro that if we activated, say, rat lymph node cells against the same rat, we got specific lysis of the rat cells and not the foreign. And if we stimulated with foreign, we got anti-foreign but not anti-self. And there was another postdoc in the lab. I said, look at this. This was in the 70s. I said, this means that there's auto-reactivity, autoimmunity in the immune system in healthy animals. He said, well, I've seen that too, but don't believe it. It's impossible. And besides, it goes against what Burnett got the Nobel Prize for. So I think part of serendipity is not just stumbling into, I think we're stumbling into things that we don't expect all the time. But I think most people, most of the time, throw out the data. It couldn't be, even if it was, we could never publish it. It's not the way, it's not real immunology. There must be some artifact, forget about it. So I think the real aspect, the important aspect of serendipity is not stumbling into something, but realizing that you have to believe your own experimental results. Now, maybe it sounds foolish to say that, but unfortunately people tend to see what they've been taught to see, and they don't see what's staring them in the face unless, excuse me, the professor has told them that that's what they're supposed to see. Well, I think that this whole story is one of taking the results seriously. The second thing you say, why is such a ubiquitous molecule feed into so many different things? How does it really tell in the case of the diabetes, to turn off the response to GAD and insulin, but not to a mycobacterial? How does it trigger a downregulation in the islets, but not in the spleen? The answer is I don't know. I don't even have a good idea of how it happens. But that goes to confirm the fact that the immune system is smarter than the immunologist. But I think that there are certainly more things going on than we have in our philosophy. And I think that if I take seriously George's question and our own results, HSP60 is ubiquitous. Why is it having these fine surgical effects? I think it means that the immune system is using very general information for making very fine effects, determinations, depending on the context. So, for example, you know, the patient comes in, has a fever and a sore throat. The physician gives penicillin. Fever is very general. Sore throat is very general. But the physician knows that the constellation, he asks a few questions about contacts, about the family, and he knows that there are two general things. He puts them together, and 95% of the time he does the right thing. So I think the immune system, and this again goes against the clonal selection idea that the immune system is like it has no preconceived ideas about what it should be looking for. It's just got a bunch of receptors, and the antigens regulate the system. If an antigen comes, the lymphocyte proliferates, has memory, and so on. No antigen, no reaction. And all the reactions are specific. That you give one antigen, you get the clones that respond to that antigen have nothing to do with the clones that respond to another antigen. And yet when we look at it, it's not so. We give a piece of an antigen, and that affects the whole response, not only to HSP60, but to GAD, to insulin, and it doesn't affect other things. And that's not the way we've been taught how the immune system works, that all these clones are supposed to be independent. But they're not independent. They're looking at each other. They somehow know that they're working together. Maybe it's because the GAD responsive and the HSP responsive and the insulin responsive, maybe they're all together in the islets where the action's going on. And so if some regulatory signal comes in, it can affect those, but the mycobacterial cells aren't there, so they're not getting affected. I don't know. It's one possibility. But the question is critical because we see it for the mice, it's life and death, and for the patients, it may be other things. And it doesn't fit the way we've been thinking about the immune system or what we've been taught, which is a wonder. I mean, if we believe the result again, then we have to start thinking, okay, how can we explore this experimentally so it's more than just an idea?
Yes, anyway, I provoked this question because I think it's a wonderful observation how we really have to trust in the results of that we obtain in the laboratory, and how you have to control very well the experiments and really, I mean, believe in what you are seeing. And actually, when we look at the way that we entered in the Hickey-Shot protein world, was it's the same way. It means that Veronica and myself, we had a student that did some experiments in transplant immunology, and by studying the T cells infiltrated the graft, he found a very strange, very high reactivity against Hitchcock protein. And we said, there is something here. Why those, I mean, this reactivity is there. It's a way of enhancing the response against the graft, or on the other way around, is a way of controlling and giving some tolerance to the graft. And that's why we started this project, I don't know, 10 years ago, right? And that's when that's.
You know the answer?
No, of course not. I mean, no, we don't know the answer, and perhaps my grandchildren will know. But we're still moving on, and we have very interesting data on this, and that's how actually we got in contact with your papers.
That's how I got invited.
Yes. So this, of course.
So you mentioned that heat shock protein peptides and heat shock protein as a whole can have both regulatory and pro-inflammatory activity. And we've been working on that too. And you mentioned also that the concentration of the peptide is important in determining whether it goes to reg or inflammatory activity. But there's probably much more than just the concentration of the peptide. And if you think that we are injecting this peptide to immune regulate inflammation like you did, and you showed beautifully in the diabetes system, don't you think there is also a risk? Because we don't know how to determine whether this peptide is going to behave in a regulatory or a pro-inflammatory way, also in vivo. And what do you think would be interesting strategies to properly select this peptide, either to induce pro-inflammatory when you want to induce like in a vaccine system or regulatory?
What are you getting? You're getting enhanced rejection or you're getting delayed rejection?
Well, you see, I think it's much more difficult to get in the context of transplantation. We haven't been successful.
What are you observing?
We observe prolongation. It depends on the peptide, and some of them, they induce acceleration of rejection. So why do you think, just putting together what would be interesting strategies to select these peptides, and what do you think the risks are of in vivo changing the phenotype of going to inflammation?
As long as it's mice, you don't have to worry.
Oh no, I mean to translate into human.
I think we have to sit down and look at the data and think about it. I don't have any.
I know, but you see, for instance, you showed IL-12, but if you look at different molecules, you also induce both regulatory and inflammatory, and we don't really know the outcome in vivo. So we just have to test each one of them and see how it works, or do you, from an evolutionary point of view, would you think about, have an idea on how these peptides would be predominantly regulatory or pro-inflammatory?
I don't have any a priori idea, but you bring up another, if we're talking about the philosophy of translational medicine, what I find, for me, very important is to work on an experimental system where you can get answers as cheaply as possible and as short a time as possible. In other words, try and work out a system where you can survey, say you've got HSP 60 and 70 and 90, and each one of them can generate 35 peptides, and you want to look at which ones have the most likelihood of doing what you want. So you couldn't do it with skin transplantation. I mean, you could, but you'd need a lot of people and a lot of mice and a lot of money. You couldn't look at all of them. So could you think of some in vitro system for screening so that you would be able to throw out 90% of them and then just focus on the real thing with a small number? So part of experimental thinking, particularly in a translational case, because as you say, at the end of the day, you want to come up with a peptide that you'll give to people. So it's not just, well, let's look at transcription factors, toll-like receptors, but if we're in a faculty of medicine, we want to do research that at some time is going to impact patients. And that means that we need model systems, but model systems that are really adequate models are time-consuming and expensive. So we, at least to my thinking, I try and work before getting into the model system, trying to do something in vitro or something that can be done simply and cheaply to cut down the number of determinations I have to make in the more expensive model, more time-consuming model. Now that means I'm probably throwing out a lot of good stuff, but I think it's better to discover something even though you've missed discovering a couple other things. And so part of the strategy of translational medicine, you know, you go from an animal model to a human situation, but before the animal model, most of these models are time-consuming, they're costly, they're labor-consuming, is to try and have something to screen as a filter, to filter out a lot of the things that you could look at, and then look at a fewer number of things in depth. It may miss, but it may get you very far.
Okay, let's give the opportunity to someone else.
Okay, first of all, I want to thank Professor Cohen for such a magnificent lecture, and to George and Veronica for giving me the opportunity of being here. I want to begin with a question related to your lecture, and then if we have time, I would like to discuss other aspects that you mentioned in your book and so on. So here, in the natural history of diabetes, be it in the NOD mice or in human beings, you think it has to do with generating at certain time and a certain site exactly this peptide by cleaving HSP60 in such a way that you generate this peptide, and this will distinguish those that turn out to be diabetic from those that don't develop diabetes. And having to do with this, what do you think happens with this peptide when you inject it subcutaneously?
When we put the peptide in serum, because subcutaneous, I don't have a way of seeing what happens to it, but you can put it in a test tube with a human serum, mouse serum. The peptide lasts about 5 minutes. So what is it doing when we inject it subcutaneously? Maybe it lasts 10 minutes. So why can we use it in the mice once, or in the humans every 3 months? It's because it's doing all these things. Now, how does it do it? What is the real anatomy of the interaction? If we would put the same peptide, if we would put it in the islets, maybe it wouldn't work. Maybe it would make it worse. I don't know. I think there's still a lot to be done. By the way, the drug companies, they don't want to know these things, because for them it can only be bad news. Because if you discover something, then they're obliged to tell the FDA. If you don't discover anything, they don't even have to tell the FDA anything. So they don't want you to do research. But this is an important piece of research. Now, do these regulatory molecules down-regulate in one site but not in another? Because part of the information is in the context. So I think that certainly when we put it in subcutaneously, it's nowhere near the site. And as I can imagine that the cells that are making the damage are not the ones that first see the peptide. There are other cells that see the peptide, and somehow they're going to where the place where the action is going on, because we see there's an effect in the islets but not somewhere else. I don't have the slightest idea how this is happening, but it's a good question that I think can be experimentally formulated. And it's important if we're thinking about adaptive therapy, or we're taking biomarkers like heat shock proteins. I think it's very natural to look at them in allograft reactions. Now maybe it's very important where we put them in the body. I don't know. But it's a very well-formed question that can be looked at.
And what about cleaving?
The cleaving that's an interesting story. As I said, there are many ways you can downregulate diabetes in NOD mice. And I don't remember exactly one of the ways that we did, but suddenly they started making antibodies to the peptide, P277. We didn't inject the peptide. I don't remember what maybe we injected a bacterium, I don't know. We did something to lower or to prevent the diabetes, and they come out making antibodies to the peptide. That says to me that we didn't invent the peptide, we discovered it, that the body is able to make it too. So the peptide is really part of the system. Now you say, why? What does that mean that a peptide is generated from another molecule? It means that the protein degradation machinery, which is very complex and very specific, is able to break down, degrade HSP60 in different ways. And some of them will generate this peptide and some of them will generate another peptide. Now philosophically, I think that that is important to the immune system, because not only what is the concentration of heat shock protein, 60, 70, 90, but what is the array of peptides that are produced, because that will tell you the state of the lysosomes in the cell. That will tell you the state of peptide transport. So maybe the immune system is gathering information about the total heat shock protein. I think it's also gathering information based on what parts are degraded and what parts are not degraded. That gives you a second level of fine understanding of the state of what's going on. So now we get back to a hypothesis. So the hypothesis would be that in different states of inflammation in different autoimmune diseases, maybe transplantation versus diabetes versus arthritis, that there'll be different sets of HSP60 peptides that are generated naturally in the particular area. Now that's a question that you can ask and answer. Either they're all the same or they're not all the same. And maybe if you're looking for something that's related to allograft and you want to focus on certain ones, is to take the ones that are present in the allograft and not present in somewhere else, and say if these are there, then maybe they're associated with that process, and I'm going to focus on them as a possible therapeutic agent.
Actually, have you ever tried since the half-life of the peptide is so short, have you tried to substitute amino acids for the amino acids?
Yeah, we substituted, I should mention it, the natural sequence has 2 cysteines, which are terrible. I mean, they fall apart and they aggregate and so on. And we substituted valines, and we just took it from there. But you're right. Now, if we made some D-amino acids, could we increase the half-life? But maybe if we increase the half-life, it won't work. I don't know. But that's something that's worth doing.
Yeah, because the big problem we have with those peptides when used for therapeutics is because they have very short half-life. And if it depends.
That's why they're safe.
Yes, but if you needed a longer, if you had a bet, we don't know. Of course, they are all open questions.
Professor Cohen, thanks for your excellent lecture, and I would like also to thank Veronica and Khalil for the opportunity of being here. And well, have some questions. I'll make 2 questions for now. One directly related to the lecture, another one more conceptual and related to all your work and your book. So the first one's very simple, it's just curiosity. You happen to have any preliminary results of a study that probably you're doing with relatives of children with type 1 diabetes treated with the peptide? And the second one is, I work a lot with autoimmune diseases as a rheumatologist. so-called autoimmune diseases. One of my feelings, the more I study, is that I have doubts if they are really autoimmune in nature, or what do we mean when we call them autoimmune? Is the immune system deranged, or is the target organ deranged and the immune system is working all right? In case of organ-specific autoimmune diseases, sometimes I really think that there's something wrong at the target and the immune system is just working out. When I think about diseases as lupus, it's so widespread, and you don't really have an autoantibody or a autoimmune T cell that is responsible for the pathogenesis, that sometimes I think that it's not really autoimmune. You have a derangement in the regulation of that function that you showed in your lecture of the immune system, which is control inflammation in the task of restoring the maintenance and so on and so on. So with these doubts, sometimes I think it's just semantic of my part, but I was very pleased to see one sentence that you said about the treatment of these diseases. Don't punish the immune system, talk to it, or talk to him. So to her, better, yeah, talk to her. Yeah. Well, but there's something in this difference, and especially talk softly to her. So then it makes sense for me now, all these questions I have, that we really punish, we don't try to understand and really so I would like to listen a little bit more of how you can elaborate on these concepts, on true autoimmunity or fake autoimmunity or whatever.
You brought up a lot of points. In passing, you say, what about children, siblings of patients? Should we vaccinate them? This is just a feeling that in looking at diabetes, but also at encephalomyelitis, and also at arthritis, it's much easier to downregulate the disease than it is to prevent it. In other words, I doubt that if the autoimmune process has not begun, I don't think that we can prevent it by giving the peptide. I think the peptide works because the disease has already activated the immune system to look for regulation. The disease itself brings together the cells that have to talk to each other. If you just take, I mean, the immune system is wandering around the body. The cells are going in the lymphatics and the arteries and the lymph nodes. They're going all around. And they're probably, if nothing's going on, they're just going at random. And to get some sort of immune decision, to get an influence on a disease, on a specific process, it may need a situation where the cells that have to talk to each other, the cells that are involved, are not disseminated at random about the body, but are already there. So I would say that the HSP60 is a specific signal when a specific reaction is going on. It's not a specific signal when nothing's going on. So it's an attractor when, or let's say it works when some other attractor is pulling everything together. That's one thing. The other things you mentioned, is it you don't know if we should call them autoimmune disease or lupus? Yeah. I think we should monitor, and then if we have some evidence that something begins, then I think would be good, because up until now we have safety, which is fantastic. Maybe one could have a study on siblings who have some progress in our dangerous antibodies without disease yet. That would be good. You bring up the question of lupus and autoimmune disease in general. Lupus is really very strange. We've been looking at lupus from various standpoints, but the thing that strikes me about lupus, it's more a reaction pattern than a specifically targeted disease. What do I mean by a reaction pattern? Well, you know, the LPR and the GLD mice that develop a lupus syndrome, it's just in interference with the FAS receptor system. What does that have to do with, why do you get double-stranded DNA antibodies and Rho and La and all that? So there are very bizarre kinds of perturbations, and you get something that looks like lupus. Or in graft versus host disease, you get things that look like lupus. So, yeah, why lupus? Or there are all kinds of things. Lupus is somehow, I would say, lupus is built into the system because you can shake the system in different ways, and out comes lupus. You're not immunizing against you can't immunize against double-stranded DNA. It's not immunogenic. At least mammalian is not. So lupus is somehow, I don't know if it's different or maybe it's teaching us about the other diseases as well. I think rheumatoid arthritis is also a disease where we don't, it's not like MS or EAE where you can immunize against a defined myelin element. So there is a world of what rheumatologists have to take care of that includes autoimmune diseases of type A and of type B and of type C, and I don't know what ties them all together. What ties them all together is the aberrant dysregulation of inflammation. So there's something in the inflammatory response that can be become aberrant at different levels and for different reasons. But I don't know. What else?
Actually, I'm pleased to hear you saying that, because I think that these are chronic, idiopathic, inflammatory diseases, that's all. And what ties them together is that they have autoantibodies, and then people dare to call them autoimmune. I think we're a little bit irresponsible on that. It's different from target-specific autoimmune diseases, in which you have the immune system destroying specifically that region. And one argument for that also is when you associate immune deficiency states with autoimmunity, like APSED, ALPS, and so on, you have usually organ-specific diseases or cell-specific autoimmune diseases, and not widespread diseases like lupus, scleroderma, rheumatoid arthritis. So maybe there's two types of autoimmune diseases, that, and the pathophysiology would be different.
We've been looking at lupus and other autoimmune diseases using an antigen microarray. So we take the robot and all the machinery for gene expression, and we spot, say, 1,000 different antigens on a slide in quadruplicate, and then we hybridize not with a nucleic acid probe, but with the body fluid, the serum or the whatever, and then we develop with anti-human IgG, IgA, or IgM, and look at the reactivities in various conditions. And but when we look at lupus, there are definitely reactivities that lupus patients have that healthy people don't have. But the opposite is also true. Lupus patients lack autoantibodies that healthy people do have. So it's another level of complication. Usually, The healthy people have, to a particular reactivity, I don't want to get into it, but healthy people may have IgM to a particular reactivity, and the people with lupus don't have IgM to that same reactivity. They've got IgG. So it's not just having an autoantibody that sees something, but the isotype is associated with the disease or not disease.
About your study with the 400 patients with diabetes type 1, have you did you see if they also produce antibodies to HSP60 molecule, whole molecule?
Could you repeat?
Yeah, the question in the clinical studies, do we see an effect of treatment or not treatment on the antibodies that the patients have to HSP60, to the P277 peptide, to GAD, to insulin? That's one of the things that the developer didn't want to study. So I don't know, but there are some. Bart Roop has done some studies looking at what is the immune response in the patients, and there are effects on the antibodies, and maybe the antibodies go with a good response, and there's effects with IL-10, but it's very unclear by the nature of clinical studies. They're just difficult to do, but I don't have an answer. Those are obvious things that should be done.
Is Bart one of the researchers involved in the phase 3?
No, the company has sent him along the way. He went with the anti-CD3 crowd.
He was the anti-CD3. Okay.
Does the chaperone, the HSP60, has any role in insulin secretion or the enhancer, concentration enhancer in the islet cells or something like that?
Apparently, yes. HSP60 is inside the insulin secretory granules, and it may be related to the way insulin is packed. But I mean, that's a lead that also should be studied. That was reported not by us, by Brudzinski. I think it even preceded our studies that she observed this. Really couldn't explain why there was HSP60 in the secretory granules and why there was a modification of presentation with the development of diabetes. So that's a whole other area. What's the fine anatomy of HSP60 expression in different organs and in different disease states?
You can go.
Did you try? Have I tried to combine your peptide with anti-CD3 therapy or something like that to diabetes?
I would favor looking at combined therapy. I think it would be good, but not with anti-CD3. I think anti-CD3 can be more dangerous than diabetes. What do you mean, why? Because that's really punishing the immune system.
But the humanized can induce also Tregs, right?
You can do all kinds of things, but why you get T cell lymphopenia, depletion of T cells. It can last for years. People get reactivation of cytomegalovirus. You have all kinds of, you can treat diabetes with insulin, but what do you treat if you have reactivation of viruses? What do you treat if you don't have any T cells? I think that, I mean, we're talking about translation and so on. I think any treatment that you want to develop has to be at least as safe as the treatments that are already there. In other words, to treat type 1 diabetes, you have to take something that is not any worse than insulin.
Yeah. actually the anti-CD3 treatments so far have been depleting ones. What Veronica is telling is non-depleting anti-CD3 that may induce tolerance or... Well, probably there is a synergy in what I think what Veronica is trying to say is that maybe synergy by doing combining therapy with other tolerance inducers.
I like synergy, but I think anti-CD3, it punishes the whole immune system. You may get rid of the very cells you need for the effect. Why do it? I can't understand why so much was invested in it. Don't quote me.
Right. Yeah, but the one that it's humanized, non-depleting that you're working on. Non-depleting. So we're not punishing. It's becoming very biblical, this discussion. But it's, yeah. By the way, why did you decide? I mean, I think that many of those questions and questions related to the intervals between treatment and all this may be very important to solve the problem when this goes to the market and will be used by normal physicians, and the adherence to the treatment may vary. You'll receive emails. Your peptide does not work. Your peptide does not work, and the point is, how can you understand why it may not work in a not controlled study? And this may be related to these questions that you're put on. I mean, how frequent you should treat, and I mean, how long that the peptide has to be there, and because then you have problems adherence of treatment and individual polymorphism related to the time of the peptide that will be active.
I mean, we know a priori that there are going to be responders and there are going to be non-responders. And the whole point of getting by the FDA is if you're lucky enough to have more responders than non-responders. But we also know, I mean, why give everybody 1 milligram? We got to 1 milligram in phase 2, blah, blah, blah.
To 1 milligram, one every 3 months?
Because in the beginning we thought we were, because we thought we were doing a vaccination. So we gave at times 0, then a boost at 1 month, 6 months, and a year, like tetanus or something. Yes. And then
I'll bring to the vaccine institute right after this.
So then we began to appreciate the fact that we're not giving a vaccine, and then we began to realize that the whole concept of a boost was not appropriate, but that it was more like a reminder. It was more like reactivating a process, which is not like a standard vaccine. And looking at the effects of C-peptide, we saw that when they got the peptide, there was an increase in the C-peptide, which lasted for 3 months, and then it fell. So he said, let's give it now every 3 months, but that's just guessing. And if we got through phase 3, then it's good enough.
Have you tempered with the dose and interval in those animals that did not respond to the initial one?
Work intranasally, or why not
try we tried intranasal, and it didn't work. And I believe that in some cases it was bad.
Alô?
So,
2.
so be careful here.
Hello, hello.
You're not doing very well with these wires and these microphones up and down. Okay, I'd like to go to a more general question. So one of the issues that you discuss a lot in immunology is that we no longer need to discover new molecules, but rather, yeah, well, I mean, not new molecule, but the most important thing is not just discover new molecules, but rather to try to understand the systemic interaction of the immune system with different systems. And I think we stand in a point in which this is really a great challenge, and we still don't know which ways to go in order to really face complexity of looking at the interaction of the immune system with different systems. So one approach that people have been trying to do is to use high throughput technologies, like doing arrays and so on. But still, the feeling I have is that when you look at these data, people still have the very determinist way of looking at them, reductionist way of looking at them, and not really interacting, looking at the interaction of these data. So I'd like to hear your thoughts about how should we try to work in this direction, trying to face the complexity of looking at system interaction and try to bring it to the training of new scientists, new generation of scientists to come.
I think this touches on what Professor Andrade mentioned, or was implied in what he was discussing. Autoimmune disease or inflammatory disease, is it a molecular problem or is it a physiological problem? Now, my bias, and it's a bias, I mean, it's the way I'm put together, I think it's a physiological problem. I think that it, again, I was quoted, and I must agree with the way I was quoted. I don't think that the disease is due to sick molecules. I think it's due to a sick system. All the molecules are good. There's no, interferon gamma is interferon gamma. But the way they're connected together, which I think you could call physiology or systems biology, rather than molecular biology. And I think if the disease is a disease of physiology or pathophysiology or systems biology, then the answer will be from a physiological approach and not from a molecular biological approach, which is one molecule at a time. And again, that goes against the way we have been educated to think. I mean, look at the efforts, untiring efforts made to look for genetic causes. So now they don't say causes, they say predisposition. Because in all of these diseases, it's very difficult to say there's a genetic cause. There's a genetic predisposition. And I would say that over the past 20 or 30 years, even in diabetes, most of the research money has gone for looking at genetics. And I don't think it's produced very much because it's not a genetic problem. People, identical twins, if one gets type 1 diabetes, doesn't mean the other one's going to get it. They've got the same genes. So it's not.
But there is a predisposition.
There's a predisposition, yeah, but more in the sense if you don't have certain genes, you're not going to get the disease. Then, I mean, all these genes that are associated with all these diseases are much more prevalent in healthy people than they are in sick people. It's just that the sick people have to have those genes in order to be sick. But you know, a hundredfold, yeah, it's necessary, but it's not sufficient. But still, let's say the reductionist program the hope is that if we understand the way the genes work, or each gene one at a time, then we'll understand the disease, we'll understand the future of the individual, we'll know everything, you know, the Genome Project. And so we have all the sequences and we still don't know anything. So we have to do the Proteome Project, we have to do the Reactome Project, we have to do metabolomics.
How to put together, I mean, how to integrate, what do you think?
No, I think that you have to do physiological thinking. You have to think systems. I mean, we used to call it physiology, now we call it systems biology. It's the same thing. Now, we have tools with high throughput, so we can look at how manipulations change patterns and so on. But you know, it's just my bias. I think they can continue another 20 years putting millions and millions of genes. It's not going to solve the problem.
Yeah, actually, I keep saying that. I mean, when you engage experiments in high throughput, if you don't have a good theory or a good hypothesis behind,
You just got a lot of data.
you don't know what to do with the data. Yeah, that's for sure. So shall we, well, the audience is always open. Priority, priority,
I think
priority.
I have a question here.
So let's go to the questions that are more general. Well, just introduce what you want. And more general, perhaps going more to the theory that you have written so much, the concepts.
I thought I've just been talking theory, no?
No, you showed experiments.
Translational.
I showed patience.
Patience.
That's translational. Well, maybe the bridge would be continuing from the last question, which you mentioned that these diseases, probably they are physiological derangements. And do you think we could define such states like lupus, rheumatoid arthritis, scleroderma as deviated attractor in the concept that you put in your book? And we might maybe start a discipline called immune physiology.
You want another name?
In different states. Yeah.
No, I agree. I think that lupus, as I said, it looks like it's built into the system because you do all kinds of different things, out comes lupus. The problem for me is understanding, I mean, if lupus is built in, it's built in to do something good. I mean, if all it made was lupus, I suppose it would have disappeared in evolution. So it has to be doing at least what we call lupus at some point has to be of some benefit. But I don't know what it is. So the hypothesis would be that the kinds of reactions that we see in lupus have a place in maintenance, repair, healing, whatever, however you want to look at it, getting rid of tumors, I don't know what. But the disease comes out when that reaction pattern is activated at the wrong time to the wrong degree and doesn't get deactivated. So the idea would be that in the course of a normal lifetime, we get something that turns on, and if it doesn't turn off, it's lupus. It turns on and off, it's just being healthy and making a response. So it goes on, it goes off, it goes on. Some people, it goes on and then it doesn't turn off, or it goes on and then it goes again, and then we say that's the disease. But I don't have an idea. I mean, in the case of diabetes, I would say that beta cells that get infected with viruses should be destroyed. And we know Coxsackie-B attack sits in beta cells, probably all kinds of things, and we probably have to get rid of beta cells as part of normal physiology. And then through viral infection or toxin or something, and in the wrong genetic constellation, there are people who don't turn it off. And those are the people who get diabetes, but probably everybody is turning them on and off all the time. And the same thing maybe with what we call multiple sclerosis. Because you talk to neurologists, healthy people happen to have MRI studies, and a lot of people have little lesions in their brains, and they don't have MS, they don't have anything. And they go through life without any. Does that mean that healthy people are having a self-limited episode of something that the brain needs for I don't know what, that when it's not self-limited, it becomes MS. So that would be the idea that the disease is a disease of physiology. It's a disease not of molecules that are no good. They're all good, but they're not regulating themselves in their interactions, and they need some help from HSP, peptide, or T-cell vaccination, or whatever.
It's a wrong behavior.
It's a wrong behavior. It's all the cells, the cells are healthy, The molecules are healthy. The system is sick. What's the system? It's a collective of interacting elements. All the elements are okay. Something's wrong with the system. It's like family therapy.
Some society sometimes.
So do you think we should rethink the strategies of diagnosing disease, looking at more physiologically? Do you think the array of looking at the repertoire of antibodies like you showed, it may be an interesting strategy, that even though if there is no cause or effect related to it, but you know that there is a disturbance in the physiology of the system, instead of looking at specific molecules?
Well, what we should do is what we believe people will give us money to study, and hope for the best. I mean, people have different points of view. People have different kinds of minds. Some people, it's very natural to think physiologically, and some people don't think physiologically. They want to go part by part. If we don't go part by part, then we won't be able to do physiology either. I think you have to know how your own brain works, what kind of friends you want to interact with, what kind of a situation you find yourself, and then rethink all the time.
Marcel. Well, I have a lot of questions, but I will begin with the first one. I read your book many years ago, and I reread it now, and I knew I was invited to come here. And it has to do with this last discussion that we are making. You state very firmly in your book that immunology is a clinical science. And my question is, if this is not due to the fact of its origin, of its history, and it began as from microbiology on the attempts to treat people and to transfer serum and so on. And this is why it has, and also morphologically, it's not so obvious, no? So it's very difficult to, it's different from the heart or the lungs or pancreas. And so this is why it has this clinical bias, not that it is intrinsically clinical. And this is why it is studied in such a reductionist way, and not because it is really part of immunology as a science. No?
I think
Clinical but not surgical.
Huh? I mean, had we, and Tauber, I think, makes it clear in his book, one of his books, had Metchnikov, if Metchnikov had the impact that Pasteur had on the science, then immunology would be part of the differentiation and development, and not clinical. And not microbiology. Yeah. So and we're all shaped by our history. What can we do?
and another question, it has also to do with your book, of course, but when Polly Metzinger stated that the immune system recognizes danger, she was speaking of the adaptive immune response. But now with the description of toll-like receptors, and the knowledge, the growing knowledge that toll-like receptors recognize self, and that recognizing self, it is associated with several diseases, how this changes your view of the immunological homunculus?
That's a good question. First, I have to reread the book. If I agree with everything I wrote, then I probably, it's time I gave up. But I'm sure that I've learned something in the 10 years. So don't ask me to repeat. I have to read and see what it says. But
I recommend it.
Yeah. The homunculus idea is a very imprecise idea. actually, I had to write a chapter in a book, and the only thing worse than writing a chapter is having to write a grant, right? Because it's just so boring, and you, so you have to, they ask you to write a review, and it's a friend, so you agree, so then you got to write a review. So usually you take a review that you already wrote, or at least the ideas, and then you rewrite it, which is terribly boring. So I had this, I had to write a chapter for a book that had to do with systems or something. And I said, okay, it's going to be in a book that no one is going to read. There's no reviewer. I can write whatever I want. It won't matter anyway. So I was sitting there looking out the window thinking about, and of course I was very much impressed as a medical student when they showed this crazy picture of the homunculus in the brain. You know, that really stuck with me. So at the time, actually, we were doing the experiments with idiotype, anti-idiotype. And what was clear, you know, Jernej had this theory that every idiotype induced an anti-idiotype, which is not true. And that's why I think the whole thing fell apart. But in the cases where you give the antigen and you get an idiotype, and then you do get an anti-idiotype automatically, in those instances, it had to do with self-antigens. So I said, I was saying, you know, maybe self-antigens are not viewed in the same way that clonal selection works on just receptors, and the antigen comes in and selects who's going to respond, but maybe there's already a picture why all antigens are not created equal. The body is looking for some antigens with more enthusiasm than with other antigens, and the ones that turned up happen to be self. So I said, if that's true, maybe it's, the immune system also has this nutty picture of you know, big thumbs and whatever, and maybe there are certain key antigens. So I said the immune system also has a homunculus. And then when I reread it, I was the only one who read that chapter after I wrote it. It looked like a pretty good idea, so I wrote it again. But it has been evolving because we're learning more about it. Actually, the idea of doing the antigen microarray came when I finished the book, because I was writing there about patterns and about the homunculus, and I said, the time is to actually look at the homunculus. And so I went from there to the microarray. So it's worth reading it. Maybe it stimulates something else.
Thank you. Well, there are many other questions probably, but I think it's time. I promised to finish at 12. So I think we're going to finish now. Irun will stay around till Friday, and then he'll be at the Congress of the Brazilian Society for Immunology. So I'd like to thank the two invited moderators, Andrade and Barcinski. Thank you for coming. Veronica for organizing all this. Patricia. And all, well, and the whole people that were involved. Patricia, thank you very much.
Thank you.